Hello everyone, my name is Florin and I work at JetBrains as a developer advocate. Normally, I would talk about things like microservices, APIs, CLIs, or our Go IDE, Goland, which allows you to develop Go applications and modern web frameworks-based applications too. However, today I want to share the journey that I had while building an FM radio station using Go. So, why did I create the project, you may wonder? First of all, I wanted to have some fun. Not only that, but I also wanted to have a different project that's not yet another microservices project or anything similar to that. I also wanted to learn something new and perhaps do something useful in the process. So since I had my home automated recently using Go and the Raspberry Pi, I decided to try to step my automation game, if you will, and do something useful for my car. And now you may wonder, how do you want to automate a car? That's quite weird, right? And not to mention potentially dangerous. So I wanted to start small. And by starting small, I mean that I wanted to send TMC data to my car's navigation so that I can take this car, drive it, and enjoy the fact that I have a built-in navigation that's capable of getting me from point A to point B with knowledge of the road ahead. Okay, so what does TMC data mean? TMC stands for Traffic Message Channel. And that data is used by your car's navigation or other devices to understand when there are traffic jams or diversions on your predefined or selected route so that you can avoid them. Normally, TMC comes over the FM radio station's capabilities, specifically through RDS. Okay, so what's this RDF stuff, you may ask? Well, you probably are familiar with RDS or Radio Data System. As it's called in the US, it's called RBDS or Radio Broadcast System. It's used to send additional data over the radio. It's used by FM radio stations mainly. And it looks something like this when you have, let's say, a screen that displays that data. For example, in my car, this data is used to display the station name, the name of whatever track I'm currently listening to, or whatever the station wants to transmit. And you can see here other buttons that allow me to select the frequency that I want to listen based on the name of the station rather than the frequency itself. With that in mind, let's go through a short introduction to radio waves so that we can better understand why we want to send this data over the air and how we can do that. As a short introduction, radio waves are a form of electromagnetic radiation. They occur either naturally or artificially. And for those artificial occurrences, let's say that us humans are responsible for. Things like satellites or your phone or my FM radio station are sources of radio waves. As for the natural ones, you can think of the lightning as being one of them. The other one can be a star or other celestial bodies. And there's a whole class of celestial bodies that can emit these radiations. Radio waves have properties. One of the properties is the speed. When you measure the speed of a radio wave in vacuum, it is considered to be the speed of light. It is equal to that. I said in vacuum because radio waves also have to pass through buildings, let's say, or mountains, or through trees, or through us humans, for that matter of fact. So each of those objects has a permeability property, which either allows the wave to pass or not, or to slow down. So that's what happens with the speed of a radio wave too. Another property is the length, or the wavelength of the radio wave. And in this case, it is measuring the peak between, or the distance between two peaks of the radio wave itself. So if we consider that our wave has multiple peaks, right? The distance between them is the wavelength. Also, we have frequency, and that expresses the measurement of time between one peak and the next one as it arrives to a certain receiver. So this is measured in hertz, and if you want to have a visualization for this, I think this will do a bit of a better job to help understanding. If we consider our radio wave to be here on the y-axis, let's say, we observe a peak of the wave as being this one, and the next one as being this one. So the distance between these peaks is called the radio wave. They travel at a certain speed, which gives them a frequency of occurrence for the peak itself. How do we broadcast using the radio waves? We can modulate the amplitude or AM and send information like that. We can use frequency modulation or FM to send data. Or we can use digital transmissions, but still have to encode that somehow. For the digital transmissions, you may be familiar or have heard of the digital audio broadcast, or DAB, or the HD radio, or HDR, if you are in the United States, for example. There are some other formats that can be used to broadcast data through radio waves, but we'll stick to just these, as we don't want to give ourselves a PhD in physics right now. Let's start with the amplitude modulation, or AM. It varies the signal strength of the carrier wave to transmit data. And in practice, it looks something like this. We have our information signal, which is this one. And we have our carrier wave, which looks very constant. So how do we transmit data using these two informations? Well, we can vary the amplitude of the signal, which will allow us to shape the peaks such that it forms our information signal. Next, we have our frequency modulation way of transmitting data, and that happens by varying the instantaneous frequency of the carrier wave. How does this look like? It is similar to what we've seen previously in terms of having an information signal and a carrier signal or carrier wave, but this time around, instead of varying the amplitude, we vary our frequency here so that we can send more or less depending on what data we want to send and how that shape looks like. As I said, there are some newer broadcasting formats too. For example, we have digital audio broadcast, or DAB, and there's the newer DAB+. These formats have been around since mid-90s, and while they are not that widespread yet, they are getting better and better adoption across the world. However, if you are in North America or in Canada, Mexico, United States, and perhaps some other places, you may be familiar with HDR, or HD radio, which is a similar standard. That's about it for our physics lessons, I would say. Let's now see how we can make some waves using Go. For those of you who are maybe impatient and would like to see our final result, this is how our system looks like when it's assembled. It consists of a Raspberry Pi device, an extension board with some additional cables, an LCD screen here, the FM transmitter, this audio jack which connects to it, more on that later, and our LCD screen for the Raspberry Pi itself, but we won't make use of that. Also here, there's a newer Raspberry Pi, so this is the Model 3, while this one is the Model 4. and I'll get to those in a second. So, the Raspberry Pi, for those of you who may not be aware of it, it's a device that is the size of a credit card and is using a single board computer as a way of working. It does not require assembly, and no, you cannot see my credit cards for comparison. It first appeared in 2012 as a means for educating children or people in areas where technology is rather expensive, so that they can have a better contact and understanding with computers and with technology in general. Since then, it's been sold in about 30 million copies or devices, and those were the last year's numbers. I suspect this year is probably closer to 35 to 40 million. And why I suspect that? Because it's being used from everything from a simple app, which maybe blinks an LED or displays something on the screen, all the way to robotics. And that makes it a very versatile and powerful device. You may wonder why. Well, there's been different releases of this device. It started from the Raspberry Pi. I'm using the Raspberry Pi 3 as a demonstration, and I've mentioned the Raspberry Pi 4. So there's been at least 4 editions, plus some additional ones which are called the Raspberry Pi Zero, which are much smaller, perhaps about the size of the LCD that I've shown you, the small one. Speaking of the Raspberry Pi, to give you some understanding of why this is powerful, the latest model has a quad-core ARM-based system on a chip, so it's something that you probably will find in your smartphone. Perhaps not the higher-end models, but still, they are powered by usually a quad or 8-core ARM-based system on a chip too. It supports up to 8 gigabytes of memory. I have the 4 gigabytes model because I was one of the early adopters, but towards the development life cycle of this device, I would say, they decided to also add the 8 gigabytes of memory version a bit later, and that was a good move, I would say. It supports one screen in Ultra HD at 60 Hz, which is impressive, or 2 screens Ultra HD at 30 Hz. So you can still watch YouTube and see the cat videos running around at 30 Hz just fine. If you want to have a look at it a bit closer, it looks like this. This is where the CPU or the SoC is. This is the memory, and this is the Ethernet controller. The GPIO part, it has an Ethernet 1 gigabyte a second connection, 2 USB 3, 2 USB 2s, 2 is a mini HDMI outputs, USB-C power, and display and camera connectors. You may see the thermal pads here covering the CPU and memory. That is because they make the contact between this case and the board, or the components, better said. And that's because it can run a bit hotter if you would like to run some certain workloads on it. Let's move on to the FM transmitter part. It is based on the Silicon Labs SI4713 chip, which is one of the more powerful devices that they have in terms of capabilities and what it can do for us. It supports RDS and RBDS, so that is a plus, and it's exactly what I needed to do for the project. It has a transmission range of up to 10 meters, or if you don't believe in general international measurement units, 30 feet, or freedom units, or whatever you want to call them. So not that much interference with your neighbors. And it receives I2C commands, so that is useful because then we can find, let's say, standard ways of communicating with it and perhaps support more devices on the target platform that we want to run. I chose the Raspberry Pi, for example, but you can run this on a Adafruit device from the Arduino series, for example. It has drivers available in C and Python, but not Go. That means that our challenge, first and foremost, will be to build the device driver for it using Go, and then move on to interact with it and do our project. So this is the challenging part of the project, I would say. Let's have a look at it. You can see that this is the chip itself, and this is the jack that it has. You can connect to the device that you have, like the Raspberry Pi, for example, using these pins here, which, yes, I had to solder myself. Please ignore that. And this is the antenna that it has. It's longer than what you can see in the picture, but yeah, as an idea, that's the antenna, and that's why there's a wire here. And the audio jack is useful because it means that it can receive or already converted audio signal into analog format, so that we don't have to worry about that. You can still send your signal using the left in and right in pins, if you so wish to do, but that would complicate the project. So for the sake of the simplicity, I chose to use this in our current demo. I mentioned I2C and sending commands to our device. How do we do that? To achieve that, I selected Gobot, which is a framework to allow you to run robots, drones, and other IoT devices. It's been around since 2012 or 13, if memory serves, and it's quite stable, I would say. It has been used in a very large number of target platforms, I would say. So you can deploy projects based on it on about 30 different platforms. So that's pretty good. And it supports a lot of other devices, so not platforms, but rather devices like the FM radio out of the box. To give you a few numbers, it supports 19 GPIO devices, 5 AIO devices, 9 SPI devices, and another 24 I2C devices. And this one is, the last part is rather important because it allows us to have a look at how other devices work using I2C, and perhaps understand what we need to do for our project, aside from having the C and Python drivers available. This is how the website looks like, and I highly recommend you that you go and visit it. Okay, so this is a presentation that probably you'll say, okay, now show me the code. How did you do this? How did you achieve this? So, without further ado, let's jump to code. Here, we have the main function of an example project that I prepared. I chose a random station name and random message that I want to send over the air. I'm using the standard logging package because I don't need more right now. And then I created an adapter telling it that this is the Raspberry Pi device that I want to run onto. Then I created the configuration for our device here, and I'll come back to this in a second. And I initialized the device driver using that configuration. I then have a worker function here defined, but I will explain it a bit in a second. That's why it's hidden for now. And I'm using the new robot function of Gobot to basically actually create our robot and then start it. Of course, I'm listening for errors, and if anything happens, then I'm gonna just break the execution. So let's come back to the worker function first. The worker function doesn't really do too much, but it's useful if you want to display data as long as your application runs. So, for example, I am displaying something on the LCD screen and then sending a message using the RDS system. Then I display another message on the LCD screen just to make sure that, it works and I have the information about the radio station and so on. And then every second I chose to basically say, okay, loop through the status of the application of the radio, and then make sure that I display something on the LCD, and in this case, it's the current timestamp. Let's jump a bit more into our driver, and to do that, let's go here. I said I'm passing a configuration, which has quite a few fields, as you can see. This means that probably I should validate that configuration first. So for that, I have this validation function, which will make sure that I'm making sure that everything is correctly configured, and if not, then I just panic, for example. After all of this is initialized correctly, hopefully, we have properties that we are sending, such as, if we look here, the transmission station frequency, which is measured in hertz, the transmission power. Don't ask me why that number, but that's the number in the manual. And if it has RDS, and if that's true, what's the program ID of that? What is the station name? And what's the RDS message that we want to send? With this in mind, let's jump to our driver, because this has a bit more interesting properties. Besides the properties that I'm setting from the configuration myself, I also have some data and interfaces provided by Gobot itself. That is very useful if we look at what interfaces we are implementing, because it allows us to understand how to develop a common functionality with other devices, and it offers a good starting point. For example, we have the config interface, which means that we can set some default configuration using the same methods, right? That's what an interface does. But not only that, we know what to expect and how to interact with them. The device interface is basically pointing to the driver interface in this case, and the driver interface is the more interesting one. It allows us to set a name for our device and retrieve it. That's maybe interesting. It allows us to have a connection, a direct connection to our device. That is useful. But it also allows us to have a start and a halt method, or stop method, if you will. And those are the interesting bits, because those allow us to have a standard way both to start our device and to stop it. Gobot will automatically stop your device when it shuts down. So that is really useful to make sure that you do any cleanup that you may need to do. Let's see how this works. Let's go with the halt method first. So halt method first, this one just calls the power down feature, which sends a command. So let's jump into this one, and we send the command to power down. Now, the command to power down looks something similar to this. And if we look at how the command looks like, the send command method, well, then the send command method basically allows us to retrieve connection and say, okay, write onto our connection. And then, unless it's the power down command itself, then we can also wait a bit for the command to be processed by our device, in this case our FM transmitter, and retrieve the status of that command. So that's useful, especially if you are developing the driver itself, to know that you've sent a good command or not, but also to understand if your command had any effect or not. And since the power up function is just above, let's go through this a bit too. So the power up command actually is used in a different place. It is used here in the begin function. Now, begin function goes all the way to the start function that I mentioned earlier. And this is yet a bit more validation. We have the begin function, and then we can do a lot more things in it. But I said I will go back to the begin function to see how we can initialize the device. And if you're wondering, why am I showing you this? Well, because this is the hardest part of getting started and programming such a device. Once you are able to power it up and power it down, sending commands should be relatively straightforward. As you can see here, for example, for the reset method, or for the reset state, let's say, of the device, I'm using something similar to this. So I can write a digital message, right, to my device. But also, if I go back here and I say power up, so I send the commands to power up here, then every other command, or in this case, any other property that I want to send, are going to be similar. Once you nail those two parts, power up and power down states, then the rest will come a lot easier and smoother. Let's see how we can send the command, right? Command is a bit different in the way we send it, so it's not a digital write anymore. It's a bit different. But as I said, yeah, you can already wait for the status and so on. So that was easy. And then setting the property. Well, setting the property is not much different. We just say we have a command to set a property named set property, right? And then we do some arithmetics here to properly translate our instructions into the ones and zeros that the device expects. And then we actually send the command. And that's about it. I would like to go into more details, such as how we begin the RDS message, what we enable, and so on. How many times do we do that? But I think we are going to be rather time constrained. So instead of doing that, let's go back to our presentation. Now, you may be wondering yourself, okay, you showed me some code. I have no idea if this is actually working or not. I don't even know where the code belongs to, or like if it's the actual device that you're showing to me or not. So instead, and sorry for looking in another way, let's actually run the device, shall we? Okay, let's go back to our main here, and we can actually say start our SSH connection. Aptly named the Raspberry Pi 3 radio device. Let's go back into the folder that we have. And we can say go run main. However, before we do that, I would like to show you a bit the setup that we have so that you know for sure that this is the right thing. Here I have the Raspberry Pi device. Okay, it is all connected and so on, still working, still everything going on to it. This is the FM transmitter. This is the extension board. This is our LCD. And now when I'm gonna say start, the device will light up. Not only that, but I can go to my phone. Over here, let me focus it a bit more, and play some music from the free library on YouTube. Let me actually start it. Okay, so with the music playing and so on, you may be wondering, okay, but yeah, you're not showing anything interesting to me. How do I know it works? For that, I have a different piece of software that's called AirSpy, and it connects to, let me bring it into focus, this lovely antenna here that I have. And this one is a USB powered device. And what I'm going to show you right now is that when I power on the device, right? So I can listen to that. And it's still working. It's playing this. If I press pause, you can see that this stopped. And I would say that's probably enough. We shouldn't have any problems with anyone because this should be free music, but just in case, let's stop here. We've seen that this actually works, which was the important part, right? So, some conclusions. We can use Go for more than servers, APIs, CLIs, and so on and so forth, databases or whatever. And not only that, we can use it actually quite successfully. There's no problems with developing device drivers, in this case for something like this. As I said, there are already many more. And if Go can fly a drone, it can certainly do other things too. Gobot is awesome. I can't express my thanks as properly as I should to the maintainers and the contributors to that lovely project. Using it was really, really nice. It shortened the development time quite a lot. Not only that, but for example, I could draw inspiration from other devices to understand where I should start and stop and so on. And I could also make sense of how I should communicate with my device in the first place. Writing, as I said, the Go driver was pretty straightforward, and all my neighbors can now enjoy my musical taste. Also, I would like to issue a challenge if you want. So if you're watching this presentation and you're like, okay, I'm going to replicate this, perhaps you can take it to the next level. Imagine yourself using a smaller device like the Raspberry Pi Zero, and then getting that FM radio that I've shown you, getting this driver, and creating a walkie-talkie based on it. Get that 3D printer to give it a shape, and then have some fun. So how cool would that be? Or anything else, actually. If you're going to build anything inspired by this talk, please send out a tweet. That would be really lovely to hear. Finally, before we get to the questions and answers, I would like to show you the component list. This is the mandatory one, but well, it's not really the case for every component. For example, Raspberry Pi with 8 gigabytes, you don't really need that. You can run on a Raspberry Pi Zero, as I said. The case for it, probably you need if you go for it. This is the breakout board, or the FM transmitter in this case, that I used, and some other components that you've seen. This is the optional list. So, for example, if you want to just get started and you don't have any other equipment, I would recommend to have at least the soldering iron and perhaps the stand. That's coming useful. And some additional components from here. Finally, at the bottom of the list, you can find the FM receiver, which you can hook up to your computer. And if you don't want to, let's say, waste internet on listening to internet radio, then you can use it to listen to the classical FM stations, let's say. If you have any questions, I would be really happy to hear them out, and hopefully I can answer them. And before we can do that, I would like to say thank you for watching this presentation. I'm really happy I got to share my journey, and I hope you enjoyed it too.